In this topics video, we are going to discuss the gradient vector and the directional derivative, which are two commonly taught topics in vector calculus. And due to the fact that they are related, and in fact the directional derivative requires using the gradient vector to calculate it, many students confuse the two topics. So we're going to go through and sort out what the gradient vector is, what the directional derivative is, how they're related, but also how they are finding actually different things. So we'll see here kind of our goals outlined for us, and then there's a table of contents on where you can find things, but this is kind of a shorter packet here. So let's get started just looking at the gradient vector, and here's the definition given for us. So the gradient vector of a function, so you take the gradient of a function, a provided function f, let's say. The gradient vector of a function is a vector that points in the direction of steepest increase. That's an important thing to remember about the gradient. The gradient points in the direction of steepest increase of the function. And its magnitude, that's its length, remember, the magnitude represents the rate of the increase, or the slope, if you will. Now, some notation says here it is denoted, so the gradient vector is denoted by this upside down triangle sign. That upside down triangle with an F there means the gradient of F. And then here is a formula on how the gradient is actually found. It is the first partial derivative with respect to x in the x position of the vector, and then it is the first partial derivative with respect to y in the y position. So there it is, using your partial derivative, your little fancy d notation, and then here's the notation with the f sub x and f sub y. This is actually my preferred notation, just it's a little bit cleaner, but they both say the same thing. Now, sometimes you see the gradient vector written more formally as the gradient of f evaluated at a point xy, or the gradient of f evaluated at a point AB. And we'll take a look at what that looks like in one of our examples here. So let's start with example 1.1, finding the gradient vector in general. So to find the gradient vector of f, we need to calculate our partial derivatives. So we need f sub x, the partial derivative of f with respect to x, or if you prefer the other notation, we could write it, those say the same thing, equals, now we're going to take the partial derivative with respect to x of this function. Remember, that means you are treating y as a constant and you are treating x as your variable, which you are differentiating. So I'm going to be careful to take my derivative with respect to x. And I'm going to add that plus 0 just to highlight here. The partial derivative with respect to x of the first term is written there. The partial derivative with respect to x of the second term is written there. And then the partial derivative of a constant is 0. So just putting those little markers in so you can highlight if you're still learning about taking partial derivatives, seeing where each piece was differentiated. Cleaning this up, we'll get rid of that plus 0 since it's unnecessary. So there we have it. We have our first partial derivative with respect to x. Now for the gradient vector, we also need to find the partial derivative with respect to y. Again, let's look at it in both notations just to get used to it. Now we're back to our f function, and we are going to take the derivative of this function with respect to y. Now y is our variable, x is treated as a constant, and again, I'm going to go through and do it term by term. So I'll have 3 terms in my scratch work, but then we'll clean it up at the end. So looking at the first term, the derivative with respect to y, second term, and then the third term. Cleaning up. And at first it might look weird that the partial derivative with respect to y, the piece we just found here, I'll highlight with my little laser pointer. It looks a little weird that this is a partial derivative with respect to y, but only has x variables in the formula. That's okay. That can happen. Don't let that trip you up. So we could write, now we found the gradient vector. The gradient vector of f is the first partial derivative with respect to x in the x component, comma, the partial derivative with respect to y in the y component. I'm going to move this over. This right here that I have just written is the gradient vector of f at a given point xy. So this might also be written as the partial derivative of f at the point xy. That implies that x and y are the variables being used in the formula as expressions we have in the gradient vector. So both this notation, this is a little bit less formal. This notation is a little more formal, saying it's the gradient vector at a random xy point. Now building on that, let's look at example 1.2. I'm going to leave that gradient vector on the screen. Example 1.2 says it's about finding the gradient vector at a specific point. So find the gradient vector of f of xy. Notice this is the same f of xy in the example from above. I didn't change the function on us. So find the gradient vector of f of xy at a given point. So the first thing you would need to do if tackling this problem from scratch is find the gradient vector at xy. Find it at an arbitrary xy point, and remember that is finding your first partial and your second partial, creating a vector. Now, we already have this because this function f is the same function where we already found the gradient. So let's just borrow that work from above. So the gradient vector of f at the point xy, I'm going to use the more robust notation. Just copying down what we have written or done from the previous step. So there's our gradient vector at xy, and now we are asked to find it at this point. So this is the a, b, or the x, y point in question. So that's what we're looking at. We are trying to find the gradient vector at that given point. So notationally, we'll write the gradient vector evaluated at the point 1, 2 equals. Now, all I'm going to do is take remember, this is an x, this is a y. I'm going to take those values and plug them into our gradient vector and get myself a vector that only has numbers involved. So this will be 6 times x times y plus 2y. I'm just following the formula up above, putting below with the x and y's in place, and I'm just showing all those steps there. We'll clean this up in a moment. All right, you can use the times sign, you can use parentheses for multiplication, all say the same thing. So the gradient vector of f at the point 1, 2 is, let's clean this up and not make any mistakes here. 12 plus 4, comma, that should be 5. So this gives me the gradient vector of f at the point 1, 2 is equal to 16, comma 5. There it is. We have found the gradient vector at a specific point. That is what was asked of us in the example. Now, we haven't really talked about the context. What did this gradient vector find for us? We are going to get to that in the next example. This first example was just to help us learn how to find the gradient. Looking at this next example, example 1.3 will give us a little more context on what the gradient finds for us. Notice I have labeled here steepest ascent and then steepest descent. Just vocab words here. Steepest ascent is referring to uphill. Steepest descent is referring to downhill. If you think of your function as like a mountain that we're climbing, we want to know what's the steepest up the mountain and what's the steepest down the mountain, maybe at a given point. So let's get into this problem. It says, consider the function. So this is a new function given to us. Notice this is not the same as the previous example. Consider this function at a certain point. So we are concerned about a certain point. Compute the following. So I'm going to go through and calculate parts A, B, C, D, and D. Before we do that, let's talk about what they find. Part A is asking us to find the direction of steepest ascent. The direction of steepest ascent is found by the gradient of f evaluated at the given point. So it is a direction because it is a vector. So at the end of the day, this quantity is a vector. Looking at what part B says to find the slope of steepest ascent. So the gradient vector finds the direction, like the path you're going to take. That's why it's a vector. The slope of steepest ascent is found by taking the magnitude of the gradient vector at that given point. Remember, the magnitude gives you a scalar, and in this context, it is going to give you your slope. That scalar is going to be that slope of steepest ascent. Part C asks us to find the direction of steepest descent. That's downhill. The good news is we'll have done the majority of the work by the time we get to that question. But the direction of steepest descent is the negative gradient vector at the point in question. So part B, and I'm going to organize these a little bit better. I know I'm kind of getting squished here. So let's just move these over for a minute. Let's take a minute to highlight. These are the things we're finding. So in part A, we'll find what's labeled. Part B, we'll find what's labeled there. Part C, we'll find what's labeled there. And then in part D asks to find the slope of steepest descent. And the slope of the steepest descent can be found by taking the negative magnitude of the gradient vector evaluated at the point in question. And I'm just going to highlight, remember what these quantities are going to represent at the end of the day. So I've kind of created a shell there on how to answer each of those questions, what we're going to look for, and now we're going to actually go through the process on how to do that. So let's start our process on actually finding each of these elements. So once again, part A asks us to find the direction of steepest ascent. The direction of steepest ascent is found by finding the gradient vector and then evaluating it at the given point in question. That's what we're looking for in part A. I'm going to put in just a little separator line as we begin our scratch work here. So step 1 is to find the gradient vector, or if you prefer the more robust notation, you can say find the gradient vector at xy, but that is kind of implied. Remember, to do this, we find the first partial with respect to x and the first partial with respect to y. So now we need to go on a hunt to do that. I am just off to the side over here going to make note of what my function is. So my function f, instead of putting f of xy, I'll just use shorthand. My function f is the following. I just want to have it on the page as we scroll down. So making sure I copied it down right. And the point in question is at -2, -1. So this is just kind of some organizational. So we have that as we go on our scratch work. So to find the gradient vector, again, we're going to look over at our function f and take the partial derivatives, right? So we're focused on our function f over here, and we need to take the partial derivative with respect to x. This is going to be 8x minus y cubed. And then we are going to take the partial derivative with respect to y. Again, we go back to the f function. We restart at the f function. The partial derivative with respect to y, the first term is 0, since we're treating x as a constant. And then the second term is 3xy squared. So cleaning that up gives negative 3xy. Oops, negative 3xy squared. There we go. So putting it all together, the gradient of f at xy can be found using the following formula in our vector. Now we are asked to evaluate this at the point -2, -1. So we just go now and plug in our x and y values to the gradient vector. And then we'll simplify and clean up. I'm just making sure I'm plugging everyone into its appropriate spot. Depending on where you go to school or where you're studying, you may get to use a calculator on an exam or not. This is why I go through this without using a calculator. I show my setup, I show where I put parentheses, and I know it takes a little longer, but I want to walk you through the simplification process just so you get that practice with no calculator, not messing up your order of operations. Now be mindful over here, if you're doing this by hand, -1 cubed stays -1. But there's a negative in front of it, so then it will change to a +1 in your simplification. And then I should get 6 over when I clean up the y component of this gradient vector. And at the end of the day, I wind up with a vector. Oops, off the screen. There we go. -15, 6. I want to put in just kind of an analogy sentence. What did this find? First of all, though, this is what we were asked to find. So we are done with what we found. But let's interpret it just to help with our understanding. So what is the meaning of what we found? And I'm going to put it in context. I'm going to pretend F is a mountain just to give us some context here. So if you are standing on mountain X, if you are standing on mountain F, so if you are standing on this function, this mountain F, at the point -2, -1, and I'm actually going to move this off to the next page just so we're not writing over that page number there. So let's continue our meaning. What does that gradient vector mean? If you are standing on mountain F at a certain point on that mountain, the direction that would result in the steepest uphill, so the direction that would result in the steepest ascent or steepest uphill is this vector. So think of that vector as like the path or the trail you're going to take. So if you're standing on mountain F at a certain point and you want to walk the steepest uphill you can at that moment in time, you would need to follow the direction of that vector. Now, keep in mind, the second you take a step, now you're located at a new point. You would have to then recalculate what's the gradient to take you up the hill steepest, right? Steepest isn't always a straight line. Sometimes you have to turn, and maneuver your way up. But at a certain point, this finds for us the steepest uphill. Now, part B asks us, what is the slope of steepest ascent? So I'll just recap that. The slope of steepest ascent, again, at the point you are standing at. How do we find the slope of steepest ascent? Well, we take the magnitude of the gradient at that point. And we know the gradient at that point. We already found that in the first part in part A. So we are finding the magnitude of this vector. And remember, this is just our Pythagorean theorem. -15 squared is 225. plus 36. Just checking to make sure I didn't mess up anywhere since I'm trying to go through this. No calculator at all. The square root, oh, I made my square root sign too big. The square root of 261. So let's just talk one more quick second. What did you find? This is the slope of steepest ascent. So this is the steepest slope that you can find if you're located at the point -2, -1. So let's take a minute to recap what we actually found. What I'm going to do is I'm going to go back up and copy and paste that sentence we wrote before, and now we're going to add to this meaning. So I'm just going to bring down this sentence from part A, and we're going to add to it. So let's get it on the page there. If you are standing on mountain F at that given point, the direction that would result in the steepest ascent is that gradient vector, -15, 6, and your slope is the square root of 261, excuse me. So the square root of 261, which is what we found. So this portion was found by finding the gradient vector at the point -2, -1. And the slope was found by taking the magnitude of the gradient vector at -2, -1. So this is how we find those two quantities. And hopefully that sentence helps you with the interpretation of what you're actually finding. You'll notice here in my packet, I had to add in some blank pages. I just didn't have enough room. So we have some blank pages going here to answer all these questions. So part A and B are related, but notice they found different things. Part A found the direction, which is a vector. Finding the magnitude found a scalar, which was the actual slope. Let's look at part C then. Part C asked, and I'm just going to summarize what part C asked. Part C asked us to find the direction of steepest descent or downhill at the given point. And again, still talking about that mountain F. So part C asked us to find the direction of steepest descent at this point. This is found, so my scratch work, this is found by taking the negative gradient vector at that point. We already have this portion. We found this portion in part A. We have that. So what we need to do is just adjust it. The negative gradient vector. I'm just copying down the answer from part A. Distributing that negative in will give us the following. So this vector right here, this vector is the direction of steepest, let's write steepest descent again at the desired point where you're standing. Now part D asked us to find the slope, so let's summarize that, the slope of steepest descent. Right? If you're walking downhill, what's your slope going downhill? And this is found by taking the negative of the magnitude of the gradient vector at the desired point. And remember, this quantity was found in part B. So all we need to do is find the negative of our part B answer. So let's interpret parts C and D in a sentence. Let's just get an interpretation just to make sure we understand what exactly we found. Interpret parts C and D. Let's check out their meaning. And I'm going to use that analogy of a mountain again. So let's say if you are standing on mountain F, the function, right? On mountain F, or on mountain F of xy, if you want to be more formal with your notation. If you're standing on mountain F of xy at the point -2, -1, then the direction, or the path, you could say, the path of steepest descent, steepest downhill, that's what descent means, and I just need to scroll back up real quick to remind myself what that vector was. So that vector that we found in part C, that is our direction or path of steepest descent, and the slope will be negative square root of 261. And it makes sense that the slope is negative because you are going downhill. So that is what we actually found with the gradient vector. We've done kind of 4 examples of what the gradient vector can find for you. It can find many other things, but these are just 4 things it can find. It can find the direction of steepest ascent, the magnitude of it can find the slopes, and then you can apply it as well for steepest descent. So now let's talk about the directional derivative, and we're going to see why this is different than the gradient. But you will see that the gradient is used to find a directional derivative. So let's just read here what it says. The directional derivative of f of xy. So again, think of f as your mountain. The directional derivative of your mountain f measures the rate of change of the function in the direction of a certain vector. Think of your vector as your path. And it is defined by the following. So we use this like weird little notation, this d sub u of f, and it can be calculated by taking the gradient of f dot product with this u vector. Now, this u vector is defined below. U just needs to be the unit vector of the direction you're trying to walk. So that's part of the definition. We need to make sure we are walking, the path that we're going to walk is in fact a unit vector. Now, a quick note on notation. Sometimes you will see the directional derivative written again in a more robust notation. The only part I've added in here is that you are going to evaluate it at a certain point. So using my analogy here, I'm just going to write a quick sentence of what the directional derivative finds for us. So if you are on mountain F, if you are standing on mountain F, so that's your function, you're standing on mountain F at the point AB. So you're standing on mountain F at a certain point, AB, and you decide to walk. So now you're just standing on mountain F at a certain point and you decide to walk in the direction of V. We'll just say some vector V. So there you are, you're standing on the mountain, you're at a certain point and you see a path and you go, oh, I'm going to walk that way. The directional derivative at that point finds the slope of your chosen path. Right? So you're standing on the mountain at a certain point, you see a trail and you say, oh, that trail V, I'm going to walk up that trail and I just want to know what my slope's going to be. That's what the directional derivative will find for you. Hopefully the wording makes sense. Directional in that you're going to pick a certain direction, and then the derivative, meaning it's going to find your rate of change in that direction. So the directional derivative does find a scalar because it's finding a slope. Now, how you find the directional derivative involves a couple of players. It involves the gradient, and it involves the unit vector of your chosen path v. So you need to make sure your chosen path is expressed as a unit vector, and we will make sure to do an example of this. So let's get into that. So example 2.1, here is the directional derivative with a non-unit vector. So all that's saying is, hey, be mindful, we're going to maybe have to turn something into a unit vector. So here's our question. Find the directional derivative of your function f at a given point in a certain direction. So what I usually like to do first, though this isn't an order you have to go in, I like to find u, which is the unit vector of v. So I put my little vector marks. So v is your chosen path, right? You're going to walk this path, but we need to turn this into a unit vector. So to get a unit vector, first thing we need to do is we need to take the magnitude of v. Remember, this is just our Pythagorean theorem. Since there are no negatives involved, I'm just not putting square parentheses. This is the square root of 25, which works out to be 5. So the unit vector, u, and I kind of got lazy and left my little vector signs off. Sorry about that, but those are vectors we're dealing with. The unit vector of v, sometimes written as v hat. Some people use a notation v hat to represent a unit vector for a specific vector. So if you use that notation, you could call it v hat. But this is found by taking vector v and dividing it by its magnitude. So you take vector v and divide each component by its magnitude. So we have our vector u. We need to hold tight on that. We need to just keep that vector around and go on and continue doing the rest of our scratch work. So we found our unit vector. I'm just going to go down to the next page. Off on the side here, just so it's on the next page, I'm going to take a moment and write down what our function actually is, just so I don't have to scroll. And I'll scroll down in a moment. So I just kind of wrote down on the next page. That's our function, and that's the point in question. The next step we need, though, is we need to find the gradient vector of f at the point given to us at 2, 1. So finding the gradient vector, we need our partial derivative pieces. We need to find f with x, the derivative of f with x. So I took the partial derivative with respect to x of the function that was given to us in the problem there. Just checking to make sure I don't have any errors. We don't obviously need to put that 0, so I'll just clean it up. Let's find the partial derivative with respect to y now. Again, we're doing that of the original function f. We're taking our partial derivatives, treating x as a constant, treating y as a variable. Awesome. So there is our gradient. I'm going to just summarize. This is our gradient vector at the point xy. I put the f sub x in the first spot, and I put the f sub y in the second spot. Now we need to find the gradient vector at the given point. So we actually need to go through and calculate the gradient vector at the point 2, 1. So we would plug in the y's where they go, and we would plug in the x's where they go. Again, trying to do this with no calculator, as I know many calculus classes don't allow the use of calculators on exams, so you might be expected to do something like this without a calculator on an exam. Oh, let's clean up a little slower here. And just making sure no errors. So there is our gradient vector at the given point. So now that we found our pieces, our goal is to find the directional derivative. I'll just say find the directional derivative in question. I'm not going to repeat all of the nuts and bolts here. Let's just find the directional derivative that is in question. Remember, to find this, the way we write it is d sub u of f at the given point, and that is going to equal the gradient vector at that point dot product with the unit vector of the path or direction you are traveling. So putting in our values, we're taking the directional derivative in the direction of u of the function f at the point 2, 1. That requires taking the gradient at the point 2, 1 and dot producting it with the unit vector of our path. Putting our values in, we have our gradient vector. We found that in the previous part. We also have our unit vector, right, of our path, and that was found first. And this is the calculation we need to make to find that directional derivative. Dot producting, remember, means you multiply the x coordinates together, and then you multiply the y coordinates together, and then you add those quantities. So multiplying the x coordinates together gives me, negative 9/5, plus multiplying the y coordinates together gives me negative 104/5, for a final answer of negative 113/5. Let's take a moment now. We have our final answer, so that is what's asked of us. But let's take a moment now to interpret this, just to make sure we understand exactly what it is we found. So let's go back to our mountain analogy. So what is the meaning of what we found? If you are standing on mountain F, and you walk, at point 2, 1. So you're standing on mountain F at the point 2, 1, and you walk in the direction. So think of that direction as like your path or your trail, if you like this mountain analogy. So if you're standing on mountain F at the point 2, 1, and you walk in the direction of that originally given vector, your slope will be negative 113/5. That is an interpretation of what you found in the directional derivative. This piece is what is found for you by finding the appropriate directional derivative, right? It is a directional slope or derivative. So take a moment just to test your understanding. Let's think about this context. If you're standing on a mountain, F, at the point 2, 1, and you walk in that given path of 3, 4, that vector, are you going uphill or downhill at that moment in time? And if you said downhill, you'd be correct. We know we are walking downhill because our slope is negative. A negative slope indicates that we're going to be walking downhill on this trail. And finally, we'll do our last example. Example 2.2 talks about the direction of no change. So what that means, I'm just going to explain what that means, is imagine, again, you're standing on mountain F at a certain point, and let's say you hurt your ankle or your leg, and you want to keep walking, but you don't want to walk on any slope. You don't want to walk uphill or downhill. You just want to walk flat. That's the direction of no change. So our job is to figure out what direction would that be. So you're standing on your mountain F at a certain point. Your job is to find what trail or path should you walk so that your slope will be 0 when you initially start. So to do this, it's a little bit tricky. It takes a little bit of faith in what we're doing to do this. So first, let's find the gradient. Let's find the gradient of f at the point in question. Notice I used a lot of 1s and 2s in our points because I'm going through this without doing a calculator or a heavy calculation. So I tried to keep the numbers just simple for us. That's the only reason there's a lot of 1s and 2s. So first thing then, to find the gradient, we know we need to find our partials, f with x. There's your function up there. Take the first partial derivative with respect to x. Find the partial derivative with respect to y. Summarize it all in your gradient vector. So your gradient vector at an arbitrary xy point is the following. Now specifically, we need our gradient vector at the point we're standing at, the point 1, 2. So this gives 2, 4. Okay. So just getting rid of that scratch work and summarizing what we found, we have the gradient vector evaluated at our desired point. And now your job, you're being asked to find the direction of no change. So you're going to find the directional derivative of your function at the given point. And I'm just going to write it in notation. And this is the piece you, no pun intended there, you are trying to find. You're trying to find that unit vector u that will take you in the direction of no change. And remember, the direction of no change means that your derivative, your slope, is going to be 0. So our job is to say, okay, we need the slope 0 to equal the gradient vector dotted with some unknown u vector. We need to find that u vector. Now, keep in mind, there's more than one answer for u. There's actually 2 different directions for u, but we won't get too much into that. We're just going to learn how to find one of the appropriate directions. So this is done through a little bit of trial and error and some guessing and checking here. Your job is to find x and y. So your first thing is to find a direction u in the form of a vector. Your job is to find this direction that results in a 0 slope. So first thing we're going to do is just find any direction that works. Then make sure u is a unit vector. This is kind of the tricky way to do this. So first, don't worry about it being a unit vector. Just worry about finding a vector at all. Then we will change it to a unit vector. The reason we don't need it to be a unit vector for the calculation, so this is kind of an important part. It is true that the directional derivative requires a unit vector to appropriately calculate it. But because we're setting it equal to 0, 0 is that magic number where we don't need this to be a unit vector to get it to equal 0. We need, so let's do that dot product. All we need, I'll recopy down what we wrote so we can see it. All we need is 2 times x plus 4 times y. I've just computed this dot product. That's all I did there. All we need is for that to equal 0. And this is that part 1. Find any xy that work. So I believe, and just looking here, I believe if x is 2, I am just picking numbers here. If x is 2 and y is -1, I'll say this works. Now, I picked these kind of smartly. I looked at the values up here and I just found 2 numbers for x and y that would work. Let's just verify that this is true. Verify that my educated guess works. So does 0 in fact equal? I'm going to follow this formula here, but I'm going to plug in the x and y that I made up. And again, I made those up out of my head using an educated guess just to show you the concept here. Is that true? And definitely it is. So we'll say, okay, that is true. So a direction of no change, right? 0 slope, that's what no change. A direction of no change is 2, -1. That is one possible direction of no change. I could have used maybe a -2 and a +1. There's a second potential direction of no change. I just picked one of them because that's what the problem asked me to find. So I found a direction of no change. Now, make sure it's a unit vector. Make it a unit vector. So I have my vector, I'm going to call it v. I'm going to find the magnitude of v. So now I'm going to make this a unit vector, or remember, if you use that v hat notation to represent the unit vector v, that's fine. So what did we find? Let's just summarize. This is the answer to the question, though. They asked you to find the unit vector, a unit vector that resulted in no change. There's also the other direction that would result in no change, and I'll highlight what that means in a minute here. But to summarize, a direction to travel that would result in no change, or if you prefer to think about it, a 0 slope, is this vector, and it is in fact a unit vector. And just to add, remember how I said another direction would also work? I'll just add that in. Another possible direction would be, and it would be the opposite, the negative of the vector I chose. So the negative of the originally chosen vector. And definitely is an exercise. If you're uncertain why that works, double check that. Find the directional derivative of the function at the given point and use this as the unit vector and confirm that you will in fact get a 0 slope at the end of the day.